You know that feeling? You're sitting there in an interview room and the whiteboard is just staring you down.
Oh, yeah. The sweaty palms, the racing heart, it is terrifying.
It really is. But then the interviewer hands you an AI or machine learning engineering coding problem, and this massive wave of relief just washes over you because you actually recognize it.
Right, like you've seen this exact pattern on Leet code or something.
Exactly. So you grab the marker
Yeah.
and you immediately just start writing out the absolute, perfectly optimized, lightning fast solution.
You feel like an absolute genius in that moment.
You drop the marker,
Yeah.
you're like, nailed it. I actually did this early in my career. I knocked out a hard problem in like 5 minutes and thought I
Yeah.
was a total lock for the job.
But let me guess. You didn't get the offer.
Nope, didn't get it. And here is the major secret we're unpacking today, jumping straight to that optimal solution. It's actually a massive red flag.
It really is a painful lesson to learn. And I know that sounds, well, incredibly counterintuitive to anyone prepping for these roles.
Right, because we're conditioned to think the technical interview is just, a race to the finish line.
Exactly. But from the interviewer's side of the table, instantly writing down the perfect code doesn't look impressive. It usually signals blind memorization.
Like you just crammed the night before.
Yeah, it tells me you can regurgitate a solution you memorized, but it doesn't tell me how your brain actually works when it encounters an unknown variable. What actually gets candidates hired in AI and ML roles is the ability to start simple and evolve a solution step by step.
So process matters far more than just the final answer.
100%. Process is everything.
To really understand this, we're doing a deep dive today into a stack of ML interview rubrics, technical recruitment guides from top tech firms, and a few foundational algorithm research papers.
And our mission today is to uncover exactly why process beats memorization. We're going to build a mental model that completely changes how you approach these interviews.
To do that, we're bringing in a classic interview hurdle, the Maximum Subarray Problem. Let's set the stage here.
Go for it.
You are given an integer array. For example, let's use the array 2, -1, 3, -2, 4.
Okay, got it.
Your task is to find the maximum sum of any contiguous subarray, meaning a slice of the array where the elements are sitting right next to each other. You can't skip elements.
Right, they have to be sequential.
Yeah. So in this specific case, if you add up that entire array, 2 minus 1 plus 3 minus 2 plus 4, it outputs 6, which happens to be the maximum possible sum you can get.
Now, before we even think about writing a line of code for that, we need to build that foundational process.
Because the initial reaction for a lot of candidates is to immediately start typing or writing.
And you have to resist that urge completely.
So I want you, yes, you listening to this right now, to literally pause and think about how you will solve this interview coding question.
Just stop. Before you worry about the absolute best way to do it, just think about how you would approach it from scratch using nothing but raw logic.
And while you're pausing, my co-host here is going to prompt you with a few structural questions to guide that thinking.
Yeah, so first, how many subarrays actually exist in an array of that size? Second, can you generate all of them programmatically?
Good questions.
Third, if you can generate them, how do you compute their sums? And finally, what would the time complexity of that approach be?
We're trying to force essential combinatorial thinking here.
Exactly. It is the absolute bedrock of algorithm design.
Hold on to those 4 questions for a second. Let those simmer in your mind. Because while you think about the underlying mechanics of that array, let's officially set the stage. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here, we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and applying your knowledge to real industry projects.
Okay, assuming you've thought through those structural questions, we need to talk about what happens the moment the silence in that interview room ends.
How do you verbally approach this?
Right. This is where we transition from silent thinking to what the recruitment guides call the think aloud model.
Oh man, this is where I totally messed up in my early interviews because you aren't just being graded on the code on the whiteboard.
No, you're being graded on the audio track that accompanies it.
Yeah, you're proving that you're someone they actually want to collaborate with on a Tuesday afternoon.
That's the perfect way to frame it. You have to bring the interviewer along for the ride with you. And that starts with what we call the level 1 brute force code.
Level 1. So What do we actually say out loud?
You must explicitly state to the interviewer, to find the maximum subarray sum, I can generate all possible subarrays and compute their sums.
That phrasing is just, it's so deliberate. Generate all possible subarrays.
It leaves absolutely no ambiguity about your starting point.
Because it proves you understand the fundamental mechanics of the problem before you try to be, like, super clever.
Exactly. So what does that look like in code? You need a starting point and an ending point for every possible slice of the array.
Okay, so that means setting a start index, which we'll call I.
Yep. Then you need an end index, which we will call j.
And finally, you need to find the sum of all the numbers from I to j.
Right. Let's visualize this and trace it out.
Okay, if I'm writing this out, the code logic requires 3 nested loops. I have an outer loop for I to pick the starting number.
And inside that?
Inside that, I have a loop for Dre to pick where the subarray ends. And then inside that one, I have a third loop, let's call it K, just to iterate through the specific elements between I and J and physically add them up.
3 nested loops. And here's where we get into mandatory BigO language.
Oh boy, best
You
move.
have to confidently declare the efficiency of what you just designed. Because of those 3 nested loops, the time complexity is O of n cubed, where n is the number of elements in the array.
Before we throw around big O notation like O of n cubed, let's just ground this for anyone who might be a little rusty.
Sure.
Big O is really just our way of measuring how much worse a program performs as the data gets bigger. It's the scaling factor, right? So O of n cubed means if we have an array of 10 items, it takes roughly 1,000 operations. If we double the data to 20 items, the time it takes to run multiplies by 8. It takes 8,000 operations.
That scaling factor is critical to understand, but we also have to mention space complexity, which is how much extra memory your algorithm needs to run.
And for this brute force approach.
In this brute force approach, the space complexity is O of 1. We aren't creating any new arrays to store data. We are just keeping track of a couple of basic variables, like the current sum and the maximum sum seen so far.
So memory-wise, it's highly efficient.
Yeah, memory-wise, it's great. Time-wise, it is a total disaster. You must clearly state to the interviewer, this works correctly, but it is inefficient.
Okay, but here's where I have to push back a little based on what I see in these recruitment rubrics.
Lay it on me.
If we already know O of n cubed is incredibly inefficient, like, realistically, if we fed a data set of just 10,000 users into an O of n cubed algorithm, the computer has to perform 1 trillion operations.
It would take forever.
Your laptop would literally melt before it finished. So why waste precious interview time explaining a melting laptop? Doesn't that make us look slow or inexperienced?
It is a completely logical concern, but the psychology of the interview dictates the exact opposite. Explaining the brute force approach proves that you can actually solve the problem fundamentally before you start performing magic tricks.
It anchors the interview.
Exactly. It shows you understand the raw physics of the data structure. If you skip straight to a highly optimized solution and make a tiny syntax error, the interviewer might assume you just misremembered a solution you copied from a forum.
Ah, right. They think you're just a copy-paste coder.
But if you start with the brute force, you establish trust. You prove you're an engineer who builds from the ground up, and you establish a baseline that you can measure your future improvements against.
You're building a floor so the interviewer knows you won't fall through.
That's a great way to put it.
Okay, so we've established our working O of n cubed baseline. Now we have to transition to optimization. But based on our process beats memorization rule, we aren't just pulling a rabbit out of a hat by reciting a memorized trick.
No magic tricks. Optimization is evolution, not magic. We improve the code by identifying the mathematical redundancy in our brute force code.
A mathematical redundancy.
This is the critical insight for moving to level 2. We have to look closely at those 3 loops and ask, what work are we doing twice?
Let's actually trace the math on our array. 2, -1, 3, -2, 4.
Okay, let's do it.
So let's say our I loop starts at index 0, which is the number 2.
In your J loop, the endpoint is also at index 0, so the K loop runs from index 0 to 0. It just sees the number 2, the sum is 2.
Simple enough. Then the J loop expands to index 1, which is the number -1. So the subarray is now 2, -1.
Right. And the K loop runs from index 0 to 1. It calculates 2 plus -1, which equals 1.
Now watch what happens when the J loop expands to index 2, which is the number 3. The hub array is 2, -1, 3. What does the K loop do?
Wait, the K loop starts all over again? It starts at index 0, reads the 2, moves to index 1, reads the -1, moves to index 2, reads the 3.
It adds 2, then -1, then 3. We are throwing away the work we just did.
Exactly.
In the previous step, we already figured out that 2 plus -1 equals 1. But our K-loop is totally ignoring that past work and starting from scratch.
You found the redundancy. Every single time the subarray grows by one element, the K-loop recalculates the entire sequence from the very beginning.
We're recomputing the exact same sums again and again.
And optimization is simply removing that redundant work.
This is like keeping a running tally on a calculator as you shop. The O of n cubed method is like emptying your entire grocery cart to recount every single item from scratch every time you add a new apple.
That is a perfect analogy.
Right. If you have 50 items in the cart and you add one banana, you take all 51 items out and scan them again. That is computationally exhausting.
It is. So, to move to the level 2 optimized solution, we just stop emptying the cart, we drop the third loop entirely, the K-loop is gone.
Wait, how does the code actually change then? We just rely on I and J.
Yep. We keep a running current sim variable within the J loop. As J expands the subarray one element at a time, we just add that single new element to our existing current sim.
Oh, wow.
We reuse our previous computations. It's just basic addition applied smartly.
Let me ask you this about the complexity then. Obviously, eliminating that third inner loop means our time complexity evolves to O of n squared, which is a massive improvement over a trillion operations.
Huge improvement.
But why does the space complexity remain O of 1? If we're keeping a running tally, aren't we storing more information?
It's a really good distinction to make. Space complexity measures how much additional memory scales with the input size.
Ah, okay.
We aren't creating a new array to store every single running tally. We are just overwriting the same variable in memory. Current sim just updates its value.
So whether the array has 5 elements or 5 million.
We still only need one tiny block of memory for current sim and one for maxim. The memory requirement stays flat, which is what O of 1 means.
Makes total sense.
And you explicitly explain this evolution to the interviewer. You say, we reduced one loop by reusing computation.
What we are really doing is establishing a universal framework here. Since we've seen how to optimize this one specific array problem, we need to extract the underlying blueprint so you can apply this logic to literally any problem the interviewer throws at you.
We're building your default thinking engine. And the framework from these technical recruitment guides boils down to a 4-step sequence.
Let's hear it.
Step 1, start with brute force. Step 2, identify inefficiency. Step 3, remove redundancy. Step 4, improve complexity.
Brute force, identify inefficiency, remove redundancy, improve complexity. I really like how systematic that is.
It keeps you grounded.
And it generalizes across different data structures. This isn't just for maximum subarray problems.
It is a skeleton key. This specific pattern, starting with an exhaustive search and then systematically removing repetition, is the exact same logic you will use to solve general Subarray sum problems, sliding window problems, and prefix sum problems.
So the philosophy is universal.
Always. The underlying philosophy is always try everything, locate where you are repeating yourself, and remove the repetition.
Which brings us back to what we talked about at the very beginning, the common mistakes. The deadly sins of interviews that get candidates rejected even when they write code that runs perfectly.
Yes, let's list them clearly so they are burned into your memory. Number 1, jumping straight to the optimal solution.
Huge red flag.
Number 2, not explaining the brute force approach first. Number 3, ignoring time and space complexity during your explanation. And number 4, blindly memorizing patterns without understanding the underlying evolution.
Let me put you in the hot seat for a second. Is this 4-step framework specifically for when you panic and don't see a clear pattern right away?
What do you mean?
Like, you look at the whiteboard, your mind goes completely blank, you don't recognize the problem from your practice sessions, and you just need a lifeline.
Oh, absolutely. It is your ultimate safety net for exactly that situation. When no pattern is immediately visible, starting with an exhaustive brute force search and eliminating repeated work step by step prevents you from freezing.
Because freezing is the worst thing you can do.
Right. You don't need to wait for a stroke of genius to strike. You just rely on the mechanics of the framework. Generating every possible combination, the brute force is almost always obvious.
You can always write a brute force.
Exactly. From there, you just trace the variables and start looking for the redundant work. It turns a terrifying test of insight into a calm, mechanical process.
That makes the interview feel much more like a regular day on the job rather than a pop quiz.
Which is exactly what they want to see.
Let's pivot slightly, because we're preparing for AI and ML engineering roles specifically. How does this data structures and algorithms logic connect to the broader systems we work with in machine learning?
That's a great question.
Because sometimes candidates feel like GSA is just a pointless hoop to jump through that has nothing to do with building actual AI models.
It connects directly, especially when you look at system architecture, how we handle data at scale. Let's draw a line between DSA and SQL, which is fundamental to ML pipelines.
Okay, I'm with you.
In machine learning, you are constantly querying massive databases to build your training sets. In SQL, we write optimized queries to reduce unnecessary data before it ever reaches our models.
Right, filtering out the noise.
Exactly. And in DSA, we optimize algorithms to reduce unnecessary computation inside the application.
So both operate on the exact same core principle, extreme efficiency.
Whether you are dealing with a terabyte of database records or a nested loop in Python, you are hunting for waste.
I want to dig into why this matters so much to the companies hiring us. It's like adding a strict where clause in a SQL database query to filter out junk data before processing.
Great comparison.
If you forget that where clause, you pull down millions of rows you don't need. In our array problem, removing that third nested K loop was our where clause for bad computation.
It really
We
was.
just filtered out the redundant counting. If we don't do that in the real world, the stakes are actually pretty high, right?
The stakes are incredibly financial. An O of n cubed algorithm running on a massive ML dataset on AWS could accidentally cost a startup thousands of dollars overnight in server compute fees.
Just burning cash.
Literally, the server is churning through operations it doesn't need to do, and AWS charges for every second of it. An O of n squared algorithm, or better yet, an O of n algorithm, keeps that same company afloat.
Right.
When an interviewer tests your ability to spot redundancies, they are testing whether they can trust you with their cloud infrastructure budget.
That completely changes the perspective. You aren't just writing code to pass a test.
Yeah.
You're demonstrating that you know how to stop a system from hemorrhaging money. Which brings us to our second pause. We've evolved from O of n cubed down to O of n squared. But forward thinking is what makes a great engineer. I want you to pause again and ask yourself, can we reduce O of n squared even further?
Look at the O of n squared approach we built. We have an I loop starting at every single index and a J loop scanning forward from there. What are we still repeating?
That's the million-dollar question.
If we already know a subarray is negative, do we really need to keep expanding it? Is there a way we can track the maximum sum by only walking through the array exactly one time?
Leaving everyone with a cliffhanger. That perfectly sets up Kadane's algorithm, which achieves that elusive O of n time complexity and will be the focus of the next deep dive.
Oh yeah, Kadane's is beautiful.
But before we get there, we have to lock in what we've learned today.
To truly internalize this framework, you need to practice. The rubrics show that candidates who practice the verbal aspect outscore those who only practice typing.
That's fascinating. So here are your assignments. For guided practice, sit down and write the code to find the sum of all subarrays, not just the maximum.
Build the brute force, then optimize it to remove the nested loop.
And for homework to really solidify this.
3 tasks for homework. First, write a function to count the total number of subarrays in a given array. Second, find the minimum subarray sum. And third, write the code to physically print out all the subarrays.
And they should use the framework for all of these, right?
Absolutely. Do all of these using the 4-step framework. Brute force, identify inefficiency, remove redundancy, improve complexity.
While you're doing that homework, you need to practice your audio track.
Huh.
You have to get used to speaking the language of an interviewer without stumbling.
Yes, the audio track is key.
So here is the mandatory think aloud script you must internalize and practice saying out loud. Brute force is O of n cubed. We can optimize to O of n squared by reusing sums. This removes redundant computation. Further optimization may be possible.
Say it in the mirror, say it while you're writing the code on a piece of paper. Make that language a reflex.
Build that muscle memory.
Because when you can articulate that evolution clearly and calmly, you prove that the process is greater than the answer. You prove you are an engineer.
Let's circle back to where we started. We talk about how jumping straight to the right answer is a red flag because it hides your process. It hides your ability to optimize from the ground up.
Right.
If optimization is purely about eliminating repeated work, and the best engineers spot redundancies that others completely miss, what other areas of your coding workflow or even your daily routines are currently stuck running in O of n cubed time because you haven't noticed the hidden loops yet?
That's a great question to leave them with.
Maybe it's how you organize your files or how you parse data in your current projects. Think about it. Keep optimizing. We'll catch you on the next deep dive.